Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 10. Student, basically in lecture number 3, I think so, we covered this example, question number 3. And in this example, basically we determine the lateral torsional buckling factor or modification factor. You can say bending modification factor, which accounts for the gradient of the movement diagram. Clear? So basically here I am going to explain you another example, because the calculation of this CB value, okay, is a little bit tricky and a little bit complicated task. Okay, so most of the students basically they are confused with this, that how we can calculate. In this example, basically you see we calculate CV value for this pen, this portion 1, 2 and 2, 3. Okay, but remember, although we have a maximum movement in this diagram, basically if you watch my lecture number 3, 4, I think so, here we have basically in this case we have 1, 1, 12 the maximum movement, and at this support basically we have 200. So one may ask that why not we take that maximum movement, because when we calculating the value of CV, basically we have to use the maximum movement, and that is, you can say, M max. Now, so that's why, because we are considering that portion 1, 2. Okay, now here I am doing some other example on the lateral torsional buckling coefficient, okay, or modification factor CB, that is known. So I'm doing this example. This is a cantilever beam, and I'm covering that example from this book. There is Zaid Ahmed Siddiqi's T structure, okay, 3rd edition. Book is available on net as well as in our local market, okay, in Pakistan. Now, Zaid Ahmed Siddiqi is a professor in Lahore UT, okay, and an author of concrete structure and so many other books as well. So let's start. We have this example, clear? And you see the example. This is although a design example, but we are just only covering a part. Okay, design the beam of figure 4.22. You will see that we have a cantilever beam, ignoring self-weight and deflection. Okay, compression flange is laterally supported at points A, B and C. Now let's see the example. This is the example, and you see that this is a cantilever beam. A, C, B, D portions we have. It says that the beam is laterally supported at point A, B, C and D, I think so. The beam is laterally, or the compression flange is laterally supported at points A, B and C. Not at D point. Clear? Not at D point. Here the beam is free, this is cantilever portion. So this is an interesting example, okay, you must remember it. This is an interesting example. The beam is supported, you can say the beam is laterally braced at this point, laterally braced at this point, and laterally braced at this point, not at this point. Clear? So to do this example, okay, let's start. Okay, let's start the example. What we need, basically, we need the movement diagram for this beam. Clear? For this beam. Now if we draw the movement diagram, you see the beam here. We have a point load, we have a UDL. You need to calculate the reactions. I think so. This is the simple procedure. You have a point load at the free end. If you draw the shear diagram, it will be somewhat like this. Clear? You see at this the variation of shear force. Clear? And if you draw the movement diagram, it will be looks like this. Clear? At the right portion it is a negative, and at the left portion it is a positive. So you see that 404.32 is basically is your maximum moment, and it is just below this point. Okay, so this portion is AC portion and this portion is CB portion. Okay, so for this span basically we have a maximum moment 404.32, and for this span we have a moment of maximum that is 540. Clear? Maximum moment. So one thing you must clear when we calculating CB and we are considering this portion AC, remember this portion AC, we have to consider the maximum moment, okay, that is 404. Clear? For both this span and for both this span. Clear? I think so for CB portion there we have to consider the other moment, not this one, okay, the other value, that is where it is, yes, 540. We have to consider 540 because in that region basically, in that portion you see here, we have that much of moment. So let's see what they consider basically. Now you see, if we go back, the factor loading and the shear force and the bending moment diagram are shown in figure. Okay, your MU or M max is 540 and MU is 404. Okay, 0.32 kilonewton for portion AC. Yes, and this moment will be used for CB and BD. So that's why, okay, they considered for CB and BD that's moment, okay, that is 540 because it will count. Okay, and for that portion basically they considered 404. Clear? Now we have to move forward, and you see here that they first of all consider what portion, and these are the maximum moment. Your LB for portion AC is 7 meter. Now this is also interesting that you see basically here that lateral bracing one is here, lateral bracing one is here, and lateral bracing one is here. So for AC our LB will be, and the unbraced length. Okay, so if I show you what is LB, let me show you. Clear? Here we have basically, where is the diagram? This one. Okay, this is basically LB. You see this is girder, or you can say this is beam, and you see these lateral bracings are provided. So the span in between two lateral support, this is how we call unbraced indirectly. So this thing you must be clear. Okay, no ambiguity. Now your LB for portion AC is 7 meter, for CB is 8 meter, and for BD is 6 meter. And this is clear. LB here is what you see 7 meter, LB here is what you see 8 meter, and for BD your LB is what 6 meter. Clear? Now these are okay, the determination. Now next you see portion AC. Now they're considering the portion AC, and same like as we did in example in question number 3, basically in lecture number 3 to 4, we have to write down a moment equation. So how we can write a moment equation? This is a simple procedure. Okay, you have to just assume a section. Clear? And this section will be at a distance of x. Clear? And as you know, we calculated reactions as well. You see here the reaction is this one, 81 point, this one. So if I write the section, if I write the moment equation at a distance xx, so one can easily determine this reaction times this distance So 81 point something, okay, times x, and negative because this is, although this is positive, if I assume, and that moment due to UDL will be negative, and the total loading is 2 3, that is 5. So 5 times total distance x times total distance half. Okay, so this will give me a moment equation for this AC portion. Remember, this equation only works out for this AC portion. This means the limits of x should be greater than 0, but x should be less than, or you can say equals to, this 7 meter. Clear? This is the limitation for this equation. We still don't consider this moment. Okay, so what they basically take this value, let me check. That's fine. This is 81.56, 6.8 basically. They consider, they factor that moment. Okay, they factor this load. So if you factor it, it comes out to be 6.8, and this comes out to be 5.6. Okay, so here we see this is factored multiplied with 1.2, and this is factored multiplied with 1.6. Add up, you get this one. Okay, so this is a moment equation. Clear? And now they will use and determine MA, MB, and C. Okay, so let's see what they can do. You see here the maximum moment for this portion is, you see that is 404. You all know it. Okay, and let me remove it. Clear? And okay, now for this portion basically, and then it comes down. Clear? So this is my MA. Clear? This is my MA. Now this is my M max, sorry, this is my M max. Now I have to determine basically MA, you know, that is, this is the portion length, this is AC. Remember, AC is 7 meter. Okay, now then we have MB, and then we have what? Then we have MC. It should remember. This MA is basically what? This is MB, and this is MC. Clear? This distance, that is LB, divided by 3, divided by 4, sorry, then this one will be equals to, although from this point it is also LB by 4. Okay, and that point is also the distance of LB by 4. Okay, now we should need to consider this, for this the whole distance, for this the whole distance from the lift support. Basically we have to consider relevant distance, because this x is basically counted from this point A. So that's why you see here that M max is 404. Now MA is 132.32 kilonewton meter for a distance of x is equal to 1.7. In the same equation, okay, 6.8, if you find out the value of XA, for, look, for, let me rub it, you know, if you want to determine MA from this equation, okay, you need to plug x is equal to LB by 4. LB by 4. Now LB is what you see here, 7 meter. So just divide 7 by 4, you got 1.75. So this means that all LB by 4 values for this portion AC is 1.74. Now plug this value in this equation, you got your MA, which is you see here is a 132.32. Clear? Similarly for MB, you have to insert basically 3.50 because you have to double it. Okay, you have to double it because this distance is 1.7 and this distance is also 1.7. So that's why 1.75 plus 1.75 comes out to be 3.5 something. And then again this distance is 1.75, so you have to triple this distance for MC. Okay, so that's the procedure. I explained this whole procedure in my that lecture. So that's why they consider 3.50, 5.25. Okay, so you must know it. This is nothing, this is basically this distance is double of this one and this distance is triple of this one. Okay, because you have to consider the movement from the left side. Now this is the formula for CB. You all know this formula. Okay, what is CB formula? CB is nothing. This is from LRFD manual. I show its reference. Okay, please check it in lecture number 3 and 4. Okay, this is here we have M max, okay, plus some constant times MA plus some constants times MB plus some constants times MC. I think so. This is 4. This is 3. I think so. This is 3. This is 4 and this is 3. And here is also some constant. Let me check it. What is that constant? You see 3, 4, 3, 12.5 and 2.5. So here we have 2.5. Okay. So you must remember it. Just you have mx, you determine ma, mb, mc. Plug all the values, you got your answer for portion AC is 1.7. Remember. Now we need to jump this section CB. Now in CB, you know the maximum moment is now 540. Okay, so and then again we have to write down an equation because that equation didn't work in this portion because we don't consider a point load. Okay, remember, we don't consider point load in that equation. So if you want to make that equation eligible, you can say for this portion, you have to consider this moment. Like, let me show you. This is mx. Okay, now you have to consider section right here at a distance of this much x, and this is x, this is x, and what we have to do, we need to factor it and then multiply that PD. Remember, the distance of that point load is nothing. You can say x, the whole distance, time minus this distance, that is 7. Remember. Okay, and the limitation of x will be, remember, x should be greater than this 7, but x should be less than or equals to 8 meter. Remember, here you have to consider as this is a negative direction, so that's why you need to find out the factor load and what the factor load is. So let me check it, what the factor load is. I think so, that is 152. So here you have 152 times x minus 7. Okay, and the limitation of the x will be this one. Remember, if they are considering the section from this side, you can consider the section from that section as well, from that side. Okay, so what they did, let's see. 540 minus 118.04 into x. Okay, this is the moment equation. Now what they did basically here, they use basically this shear diagram. Okay, because you know that if we determine the shear, both these shear areas, it will give us the moment at any point. Okay, and you already did this calculation basically in your structure mechanics. Okay, so from shear area basically you can determine, if you multiply this 90 with that span, that is round about 6 meter, you got this 540. Clear? And then this is, you can say this is positive, then you have to subtract this, or either you can consider this positive, then you have to subtract it. So this is the way that how we can use. For example, if I snap it, this diagram, okay, if I snap it, let me take a snap. Okay, now let us see. Remember, if I consider a section right here at a distance x from this point, because here is my support, so that's why from support you can consider your x. Either you can also consider from this free end. Now the limitation for x, remember, should be greater than 0 but less than that 8 meters something this span is. Now if you want to determine your movement at this section x from this shear diagram, then you need, this is a positive shear, let's say, and this is a negative shear. So mx will be the shear area of this one. This span is 6 meter, so it's 6 times 90, you got 540, and as this is a negative, so that's why negative, and then I have to multiply this 118.04 times that's span, and that span is here is nothing, you see this one, remember this portion, not the whole portion, because x is varying, so times what? Times x. So that's why they write down this equation. Okay, this is x start from B and B, remember x start from this B point, not from that free end. Clear? And the maximum value of the moment will be MA, and then we have to consider basically MA and B. Remember, your values will be right there, 2 meter. Now you know the span length of this section is CB section we have, so we have 8 meter. Now if you divide 8 meter by 4 basically, okay, let me rub it. Okay, now you see that the length of this portion is LB is 8 meter. Okay, now I have to consider MA and B. Now for MA, what you need, you have to use LB by 4, and you already know 8 divided by 4 you got 2. Okay, for MB, you have to double this distance. For MC you have to triple this distance. That's the procedure. Okay, now one thing, make sure this is interesting. Okay, take MA, MB, MC values. Clear? This one will be MA. Now you see that your MA value is 2, your MB value at a distance 4. This is 2. You know the distance which is used for your MA will be 2 times for MB and will be 3 times for MC. So you got the values, just you need to insert it into the table and you got your answer. The portion BD CB is equal to 1.0. Why? This is important. This is important. Remember, you have a cantilever portion, okay, and for a cantilever with a free end, if it is not basically if it is not, you can say, braced, then in that case basically it will be what? It will be 1.0. If it is braced, then you have to calculate it, and the procedure is basically you have to use the same formula for that portion as well, and in that case the CB value will be different. But for all cantilevers having a free end, we have to consider basically your CB value is 1.0. Clear? So this is how they use CB is equal to 1.0. Now what they did basically, they make a table, and to show you the variation of the span length, versus moment versus shear. Okay, so here you see your portions, here you see your maximum moments, your maximum shears, your LB, your CB value, and this is your moment capacity. Okay, now this table is very interesting. You see the effect of LB over CB, and both the effect of CB and LB on the strength of the section or of a beam section for a portion. You see AC portion having a maximum moment 404 and a shear value of this much, but you see LB is this one and CB is this one, the capacity is this one. Now for CB portion, that is the middle portion, you see the maximum moment is 540, maximum shear, maximum LB, and